I know a lot of you guys are having trouble right now. You're looking at the integral and you're saying, how do I know what to do? You know what to do, but how do I know what to do? Well, remember, I've done more than 10,000 of these, probably on the order of, say, 20,000 of these over my lifetime. So, you know, I have a bit of a head start on the rest of you. The idea with the integration, you started, Shannon?
Yeah.
Good. Okay, so the idea of integration is we're going to give you a bunch of toolboxes. So you look, as I've said before, you have a function, you look at the derivative of the function. It's easy to find the derivative now. You should be able to find the derivative of almost anything, but going backwards is tricky. When you look at the function and say, what was the original function? What is this the derivative of? It's much harder. And there's not really so much theory at this point, so understanding is a little tricky. You really just you have to start seeing the patterns, and that takes time. And that's part of why you practice. So first, if you develop the mechanical skill, later the other skills will appear. And you'll say, I'm starting to understand why I use this technique for these kind of integrals and a different for other kind of integrals. And I know it's frustrating, so that's why you just do lots of practice. So as I said, I'll put up stuff from my book to give you more to practice. And I'll see if I can find other practice problems for you. And then at some point, you've really done them all, and there really aren't any other types left. So one of the things we're going to do today is going to involve lots of, I never would have thought of doing that kind of stuff. So in the beginning, you look and you go, how do I know to do that? The answer is, well, this is what you do. And then as you get better at it, you will develop more technique, and then at some point, you'll be showing somebody, and they'll go, how do you know to do that? And you'll say, I'm a genius. But really, you've just done it more times than they have. Any questions before we get going? No. But one of the things is, you're going to want to remember a bunch of your trig stuff. So I'm just going to put them down here again for everybody's use. So sine squared of an angle plus cosine squared of an angle always equals 1. That can be rewritten. I'm going to do this quickly, and then it'll just sit here all class. It's either this or this. Those are all saying the same thing. Furthermore, 1 plus tangent squared x equals secant squared x. So if you see secant squared, you can replace it with 1 plus tangent squared. If you see tangent squared, you can replace it with secant squared x minus 1. We're actually not really going to need that top one. So I'm going to save that space. You can have it in your notes, but it doesn't matter. So if you see cosine squared, you can replace it with 1 minus sine squared. If you see sine squared, you can replace it with 1 minus cosine squared. But sometimes you're going to want a different substitution for this, which I'll show you in a second. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. Now, I can derive the next two, or I can just show them to you. Who wants to know where they come from? Yeah, there's always a few. So, there's the double angle formula, which says cosine of 2x is cosine squared minus sine squared, but it is also 2 cosine squared x minus 1 and 1 minus 2 sine squared x. So you could rearrange this with a little algebra to get the following. Sine squared x is 1 minus cosine 2x, all divided by 2, or times a half. And cosine squared x is 1 plus cosine 2x. I'll rewrite this, it's a little neater. Okay? So if you take these and you play with them, you get these. So sometimes you're going to see cosine squared, and you're going to want to do this substitution. And sometimes you're going to see cosine squared, and you're going to want to do this substitution. And you say, how will I know? And the answer is, well, one will work and one will not work. That's really what it is. And as we do them, I'll show you, and I'll say, well, now we're going to use this one, now we're going to use the other one. So what's going to happen today is we're going to do a whole bunch of trigonometric integrals. And integrals have trig inside of them. And then you're going to rewrite the integral to be something that you can now do. Okay? By playing with the integrals. So we need a couple others for our toolbox. So do you remember how to do the integral of tangent? I think we did it in class. But let's do it again. You want to do the integral of tangent of x dx. We're going to make that sine over cosine. And now we can do u substitution. So how would I know to do that? Well, otherwise, what are you going to do with tangent? I have no idea, so you might as well try something. So you say, well, let's try this and see if it works. You can say, well, now I could let u equal cosine x, and du is minus sine x dx. So if we substitute in, we have cosine x in the denominator. Now how do I know to make u cosine and du sine and not the other way around? Well, if I let u be sine, du would be cosine, and I'd have u in the numerator and du in the denominator, and you have no idea what to do with du in the denominator. So, I mean, you can't have du in the denominator. Du has to be up in the numerator, at least for this stage of your life. Okay? So I substitute the other way, and I put u down here. And since du is negative sine x, negative du is positive sine x. And then that is just log of u. So this is negative ln of u plus a constant. And now you substitute back. Okay? One piece of chalk down. See how many I can go through today. So far, so good? All right. So cotangent would be the same way. Instead, you'd make it cosine over sine. You'd let u equal sine, and du would be cosine. So I'll let you practice cotangent on your own, because once you do tangent, you should be able to do cotangent. Agreed? Now for a fun one. How would you do secant? The integral of sex. So let's see. Well, let's say if I make it 1 over cosine. The problem is if I make it 1 over cosine, right, I'm going to have cosine. See, if I do this, this is wrong, so don't copy this. If I'm going to do this, now what? I'm not better off, right? I can't let u be cosine, and so we don't want that one. To make it cosine negative 1 is the same thing, because I need a sine somewhere. So if I'm going to have a cosine, I need a derivative of cosine. So here's something that maybe you would have thought of, but probably not. Why don't I multiply the top and bottom by secant x plus tangent x? And you go, you got to be kidding me. Well, I didn't think of it the first time either. Probably not the second time. But somebody came along, 200 years ago and said, I don't know how to do secant of x. And then some annoying math guy said, hey, here's a clever trick you could do. Because this will now become, and the answer is, how do you know you can do that? Well, I just did. That's how you know you can do it, because it works. And a lot of these, the answer is because it works. Yes, there's a reason why, and as I said, as you start to do more of these, you'll start to understand why. The answer is you can always multiply by 1. So, secant times secant is secant squared. Secant times tangent is secant tangent. The bottom is this. Okay. What's the derivative of secant? Secant tangent. And what's the derivative of tangent? Secant squared. So now you can let u be the denominator and du will be the numerator. And I know, you're saying, I never would have thought of that. I know, but now I taught it to you. There's lots of things you never would have thought of. So if I let u be the denominator, the good news is, there's really only 2 types of this. So the odds that it shows up in any real way are very small. We really can only give you secant and cosecant. So I'm going to show you secant and you do cosecant for practice. Okay? But the thing is you may need the integral of secant x for something, or you may need the integral of tangent x. Like when you're doing integration by parts, sometimes one of the parts that's left is secant x. So then you just know what this is going to become. So now we have du on top and u on the bottom. That's log of u. And now we substitute back. So that's ln of secant x plus tangent x plus a constant. So these you should be able to derive these and then you memorize them. So mathematicians tend to fall into two groups. Ones who every time they see it, they have to figure it out and derive it. And others who they've done it so often that they just say, well, I just know what it is now. Okay? And you'll be in one or the other. You're going to see this when you do. I mean, you guys are doing science. You'll see this in science all the time. At this point in these, I've seen it too many times. But in the beginning, yeah, I would sit down and refigure that one out. And then if you do it 3 or 4 times, then you know the trick. Right? So don't despair. So I'm going to copy those over here so we have those written down. And as I said, and you should practice those. And you should practice doing cosecant. It's the same trick. You just multiply by cosecant x plus cotangent x over cosecant x plus cotangent x. So this is negative log cosine x plus a constant. A small number of books will write this as positive log of secant x. I'll leave you to figure that out on your own. And this is the log secant x plus tangent x plus a constant. Okay, so feel free to memorize. Nothing wrong with that. After all, you memorized the Pythagorean theorem. Yes? Would you have to show work if this was on the midterm? I would show the work for one simple reason. If you mess it up, okay, you won't get any partial credit. There's not much you can do with this for a midterm because it's just this, right? So more likely there'll be a problem where part of the problem will have you figure that out. I was showing somebody this earlier today, where you get to a stage where this is part of the integration by parts. And there you could just say, well, I know that's log of secant x plus tangent x. Sound good? So now, let's have some fun. I know, you guys, you thought you were done with trigonometry forever, but you're not. Just when you thought it was safe. So we did something like this already, where you said, I would just let u equal sine and du is cosine, right? We know how to do that. What if this was cosine cubed? Now, all of a sudden, it's annoying. Before, it was easy, because if it was just cosine, you had u was sine and du was cosine. Well, look at those. So leave the sine to the fourth alone, and break the cosine cubed into cosine squared times cosine. I personally think these are kind of fun. They remind me of the trig identities stuff back in advanced algebra trig days. If you thought those were fun, then you're going to have a good time with these. Of course, you might not have many friends, or any friends. I'm not going to go out tonight. I'm just going to sit home and do trig identities. That didn't make me friends. Very sad. All right. Now, cosine squared is 1 minus sine squared. Now I can do u substitution. What am I going to let u equal? How do I know u is going to be sine and not cosine? Well, if u is cosine, then du has to be all of this, which is not going to happen. Okay? But if I let u be sine x, then du is cosine x dx, and this integral is now u to the fourth times 1 minus u squared du. Isn't it? Now you just distribute the u's. So make that u to the fourth minus u to the sixth u. And that is u to the fifth over 5 minus u to the seventh over 7 plus c. By the way, comment on your midterms. Some of you guys were very sort of confused / sloppy / got it kind of in the wrong spot with the phase from when you have the integral to when you don't have the integral. And you'd leave a du in here, or you had a plus c in here, or something like that. So be careful when you're doing the steps, okay? Because you don't want to get the TAs too confused. Now we substitute back. So this is sine to the fifth x over 5 minus sine to the seventh x over 7 plus a constant. And you would never have looked at this and said, oh, it's going to turn out to be that. Okay? So as I said, part of what makes integration so difficult is there's no intuitive way to look at this and turn it into that. Now, once you take cosine and you get to this step, then it might be more obvious, but not in the first step. Okay? So that was a big thing with trig altogether, is you'd see something in trig in one form and then you play with it, and now it's in a new form and it was much easier to work with. Yes? Okay, so u to the fourth times 1 is u to the fourth. U to the fourth times u squared is u to the sixth. Okay? Yes? How do you know when to do u substitution? With these problems, most of the time you will be able to get to u substitution. Because what will happen is after you rewrite the integrand, you'll have something with sine or cosine or whatever, and something with the derivative of it, and then you can play with it. Sometimes it's going to be integration by parts. And I can't give you you have to play with them and do a bunch of them until you start to see. All right? Let's do some others. I'm going to erase this in a minute. Yes? Can you do u to the fourth minus u to the sixth is not u to the negative 2 or u to the 2 or anything like that. Okay. Let's do all right. What if I just have plain cosine squared? I'm going to use an identity. So if I have cosine squared, I might use this identity right here. So yeah, well, these you should definitely memorize. I mean, you're supposed to know these. These two I recommend you memorize. Okay? Or you could derive them from the double angle formula. Okay? But I recommend that you memorize these. The only difference is sine is 1 minus and cosine is 1 plus. Why is that going to be helpful? Well, right now, you don't know what to do with cosine squared. You can't do anything with parts. With integration by parts, what happens is, if you haven't noticed, you have two terms in the integrand. So if one of them is x to a power, each time you do the integration by parts, x goes to a smaller and smaller power, and then at some point, x is gone. When you have e, on the other hand, or sine or cosine, e just keeps staying e. So the derivative of e to the x is e to the x is e to the x. That doesn't help. We're integrating it. And sine and cosine just go back and forth, from sine to cosine to sine to cosine. So you're not really getting much value out of that. So here, you can't do u substitution because there's no sign in there. And you can't do integration by parts because what would you do? So you could do this substitution, however, and make this, put the half on the outside, 1 plus cosine 2x dx. So that's your substitution. Yes? Why not use the other one? Because if you made it 1 minus sine squared, you wouldn't be any better off. Okay? So how will you know which one to do? Well, one clue is if you just have sine squared or cosine squared alone, and you don't have anything else in there, then you're going to use these. If you have both sines and cosines, you're usually going to use those, but not always. It's tricky. It kind of depends also on whether the power is even or odd. There's sort of families of these, and I don't want to do too much at once, and I don't want to get too intense because that's really for 132, not for 126. But okay, this is now relatively simple to integrate. This is 1/2, and what's the integral? Well, the integral of 1 is x. The integral of cosine 2x is sine 2x over 2. Plus a constant. Somebody's having fun. So far, so good. All right. So now how do we make this more annoying? Sure, if once you can do cosine squared, of course, you should be able to do sine squared. What if I gave you cosine to the 4th x? So this is the first one you get to do on your own. The way you're going to do cosine to the 4th, I'll give you the first step, is it's cosine squared squared. And then you're going to use that substitution. So you're going to have to FOIL it out, and you're going to have to do a substitution a second time. So this is going to take you a couple minutes. Yes?
Can you just explain one more time how you got sine squared?
How do I get, well, the antiderivative of cosine, right, is sine. And then you have to divide by the derivative of the term, okay? Because it's sort of the opposite chain rule when you're doing integrals, right? If you're doing the derivative, you would multiply by 2. Since you're doing the integral, you divide by 2, okay? All right, so that's going to take you guys about 5 minutes. Let's see how you do. So let's give ourselves some room. This will take a bunch of steps. So I'm going to erase this so I can give myself some room. As I said, it takes practice. It's very algebraic. It's lots of manipulation and stuff. So you have to be careful. So we had this. Okay. So what was our substitution? Well, the substitution for cosine squared is 1/2 of 1 plus cosine 2x. So this is going to be 1/2 1 plus cosine 2x squared. So first thing is you're going to have to square the half. So a half squared is a quarter. And it's going to be a quarter times the whole thing, so you could put it inside the integrand, you can put it outside, it doesn't matter. And then you're going to get 1 plus cosine 2x squared, so that's 1 plus cosine 2x times 1 plus cosine 2x. So you're going to have to multiply that out. So far, so good. Okay. 1 times 1 is 1. Always got that one. Cosine 2x and cosine 2x is 2 cosine 2x plus cosine squared 2x dx. Okay? So when you multiply that out, stop enjoying yourselves. It's math class. It should be. All right, so now we have to integrate this. So this integral is going to be easy. That's just x. This integral is going to be easy. So let's split this integral up. We're going to have a quarter times the integral of 1 dx plus a quarter times 2 the integral of cosine 2x dx plus a quarter the integral of cosine squared 2x dx. Okay? It's like distributing the quarter and then making this an integral, and that an integral. Yes?
Is it possible to use the identity 1 minus sine squared as opposed to?
If you did 1 minus sine squared in the beginning, you would be in the same spot. Because all that would happen, if you use 1 minus sine squared here, and you square it, you're just going to get 1 minus 2 sine squared plus sine to the fourth. You're just going to have the same kind of stuff. So what you're trying to do is get rid of the square, the squaring, and you're trying to reduce the power down to just a sine or a cosine. Because you know how to integrate sine. You know how to integrate cosine. So if you can get the powers from the fourth to squared to no power, the power of 1, then you can do it. Okay, so that's what you're trying to do. Right, this is going to require another substitution. So let's just do this integral. This is 1/4 x. That one's done. 2 times a quarter is a half. And that's sine 2x over 2. All right, so let's do this one now. Cosine squared of 2x. Well, we did cosine squared a minute ago. That's going to be now 1/2 1 plus cosine of 4x dx. How do I know it's 4x? Because it's this formula. Whatever this variable is, this is double it. So if this was 10x, this would be 20x. Okay, if this was 100x, this would be 200x. It's a double angle formula. Okay? So that is 1/2 of the integral 1 plus cosine 4x dx. And we know what that integral is. This is going to be times 1/2 of, integral of 1 is x, integral for cosine 4x is sine 4x over 4, plus c. And then you can distribute the quarter, and there's some simplifying you can do and all that stuff, but that I'm not concerned about. We're at the cosine 4x. Once again, this is the double angle substitution. So when you see this, okay, when you see the cosine squared, it's 1/2 1 plus cosine of double the angle. So notice you went from squared to non-squared, and the angle went from x to 2x. So here you get cosine squared 2x, and you get to 1/2 1 plus cosine 4x. So this is squared in 2x, this is not squared in 4x. Yes? Well, when I'm all done, right, the 1/4 is out here. Okay? So this is now 1/8 of x plus 1/2 x. This is actually 3/8 x. Okay? Sine 2x over 4 and sine 4x over 32. So if you put it in Wolfram alpha, that's what it's going to spit out. Okay? It's going to give you the final form of it, which you may not come up with, and frankly, I don't think you need to. Obviously, what if you had a cosine of a 10th? Okay? You'd have to do this like many times. So we would never ask you that, because that's just sort of sadistic. Okay? But by the way, there are patterns to this, though. So if you look at tables of integrals, or now the computers have them programmed, okay? There's a formula, and if you do this enough times, you'll start to see, and then eventually you don't have to actually do these out anymore. But this class will never go there. I'd say 4th is as annoying as it gets. So far, so good? Yes?
I just want to know why sine 2x.
Okay, so we did this last time. So if you have cosine of 2x, the antiderivative is sine of 2x divided by the derivative of 2x, which is 2. Okay, so it's the chain rule for integrating. Okay, so it's going the other way. Yes? This one. This is this. Okay? So the antiderivative of 1 is x. The antiderivative of cosine of 4x is sine of 4x divided by 4. I'm sure very few of you are able to do this, so you practice it with sine to the 4th. So I'm going to give you a similar one to practice. Okay? Question? Right. Remember, this angle is double that angle. Okay? So when I have cosine squared of 2x, okay, it's 1 plus cosine of 4x times a half. Okay? Because it's 2x's. All right, I'm going to erase this. It'll be on the video. Take a picture. Copy it from your friend. Give up. Any of those. I give you one very similar, and let's see if you can execute it this time. Then we move on to another type. Now, there's actually 2 different ways you could do this, okay? But let's practice doing it this way. So now, you're going to want to substitute for sine squared and for cosine squared. So it's the same substitutions, except you have 2 different ones. You have one for sine squared and one for cosine squared, and then the technique should be very similar. You can't have very many of these in a test. They're 15-minute problems. Okay? And nobody wants to grade them. I just write 0. If I don't see the right answers, put 0. It's all right. Don't want you to be my doctor or anyone. Yeah, you throw them in the air. Face up, A. Face down, F. That works. We'll give you the first step. Remember the first step, okay? Okay? All right. So now we could distribute this. And 1 minus cosine times 1 plus cosine is 1 minus cosine squared, 2x. This one's actually kind of easier. Do we agree? A half times a half is a quarter. And 1 minus cosine times 1 plus cosine is 1 minus cosine squared. Which, by the way, is sine squared. If you wanted to, you can make it sine squared, but you don't have to. At this stage, you could do whatever you want, but I would make it sine squared. Now, if you're really clever, you know that the double angle formula for sine of 2x is 2 sine x cosine x. You could have gotten there faster, but that's okay. I can't expect you to remember all the trig identities. Now, from sine squared, we use that identity. 1/2 1 minus cosine 4x dx. Why cosine 4x? Because that's 2x. And by the way, you don't have to convert this to sine squared. You could have made this 1/2 of 1 plus cosine 2x. It doesn't matter. In the end, you have to end up in the same spot, right? They all have to come out the same, otherwise you made a mistake. Or something funny is going on. So 1/4 times a half is 1/8. And the integral of 1, we don't even need this anymore. The integral of 1 is x. The integral of cosine 4x, sine 4x over 4. And then you can distribute the 1/8 if you want. Aren't these annoying? Yeah. You'll get there. We're going to do an easier one now. Yes?
Where did you get the half from?
Where I get the half from? Which one? This one?
Yeah, that one.
That's from the sine squared identity. Remember, sine squared is 1/2 1 minus cosine 2x.
Okay.
Yes? You mean why I get here? No, because you're going to divide by the derivative. Okay. You divide by the derivative. If you took the derivative of sine of 4x, you would get cosine of 4x times 4. Okay, so if you do the antiderivative, you get minus cosine of 4x divided by 4. The reason is when you do the derivative of this, you're going to get a 4 from the chain rule. That cancels the 4. It gets you to here. Okay? I know, you guys keep asking me that one. All right, let's do a totally different type. These are fun. Okay. What if I wanted to do that? So now, of course, you could put that in sines and cosines, but that won't help you. It won't help to put it into sine. Try it. See, what happens is people came along and they said, I'll put it in sines and cosines. They did that. It didn't work. So now you need a plan B. Okay? And somebody said, well, I know the derivative of tangent is secant squared, but I have secant to the 4th. So could I do anything with that? I only want to have secant squared because the rest is tangents. So what if I make this tan to the 4th x, and I break this into secant squared x dx? How is that going to help? Well, because 1 plus tangent squared is secant squared. So you get tan to the 4th x times 1 plus tangent squared x, secant squared x dx. Now, why don't I change the tangent? If I change the tangent, try it, and it doesn't really help. Now, why don't I change them both? If I made both of these 1 plus tangent squareds, I'm not going to have any derivative running around, because this is the derivative of tangent. So now I can do u substitution. I let u equal tangent of x, du is secant squared x dx, and I get u to the 4th, 1 plus u squared du. See what I did? There are patterns to these, as I said. After you do a bunch of these, you start to see them. Yes? That's what I did. Oh, can you always do that? It depends on, can you always split the secant to the 4th into secant squared? It depends on what else is in there. Okay? But the derivative of tangent is secant squared, so you only need a secant squared. Okay? So you want to take the other secant squared and put it into terms of tangents. So if this was secant to the 10th, okay, you get secant to the 8th times secant squared, then this would be 1 plus tangent squared to the 4th. But then you just make it 1 plus u squared to the 4th, which you can multiply out with a little pain. Because this, so you have to be pretty sadistic to make them too big a power. But that's not hard. You can distribute that u to the 4th. That's u to the 5th over 5 plus u to the 7th over 7 plus c. So it's tan to the 5th x over 5 plus tan to the 7th x over 7 plus c. As I said, you would never have looked at tan to the 4th, secant to the 4th, and said, oh, it's going to turn into this. Okay? So these techniques help you turn the integral from something that you have no idea what to do with to something that you do. And there's going to be families. As you start to play with these, you'll see it matters a lot whether the powers are even or odd. That helps you figure out which one you're going to do. I'll show you why as soon as we get this one copied down. Aren't we having fun today? This is your punishment for not coming on Monday. I know, some of you were here, and some of you were studying your biology. I hope it was worth it. But you hurt my feelings. Yeah, there's that too. You might just find this fun altogether. So this Friday when I'm staying home doing trig integrals, you can join me. Yeah. Whoever gets it wrong first has to drink, so. But it's only water, because you're under 21. All right, let's do a similar one, but not the same. Instead of tan to the fourth, secant to the fourth, what if it was tan to the third, secant to the third? You go, seriously? Haven't we done enough of these already? Tan cubed. You're welcome. Secant cubed. So what are we going to do this time? Because now if you look and you say, if I break out a secant squared, I've got one secant left over and I can't turn it into a tangent. And if I take the tans, that's not going to help. So here's another idea. What's the derivative of a secant? Secant tangent. So let's make this tan squared x, secant squared x, times secant tangent dx. How do I know to do that? Because these are odd powers, not even powers. Nope, lost one. That's all right. We'll see her next week. Now I can take secant squared, tangent squared, and make it secant squared minus 1, just like the last one. Why would I do that? Because the derivative of secant is secant tangent, and now I can do u substitution. So let u equal secant x. And du is going to be secant x tangent x. So if u is secant x, du is secant x tan x dx. Believe me, first time I went through a lot of these, it was just as hard. By the way, we've only made them x. Wait till we make it pi x. Or pi over 4x. Or if we really hate you, pi over 17. Or something really annoying like that. I would never do that. But, you know, if you just throw in some constants, it just gets messy, okay? It doesn't test whether you know what you're doing. So now, this integral becomes u squared minus 1 times u squared du. Isn't that u substitution great? Because if 1 plus tangent squared is secant squared, then tangent squared is secant squared minus 1, right? Just move the 1 to the other side from this one. Notice I'm not doing the cofunction ones. They're the same. So that's u to the 4th minus u squared du. That's u to the 5th over 5 minus u to the 3rd over 3 plus a constant. And substitute back. Secant to the 5th x over 5 minus secant to the 3rd x over 3 plus a constant. How do I know when I'm done substituting? When we mean playing with the integral. When I've got it to a point where I say, aha, either with u substitution or some of the rules I know, I can now integrate it. I know these aren't satisfying answers. As I said, if you do these, there's families of them and you start to see. Well, it's because, why is it u to the 5th over 5 all the time? Because I'm doing these cubes and squares. If I gave you higher powers, you'd get higher powers in the answer. I know, they're really fun. All right. You got this one? Let's do, should I do the one I did before? Do that. A tan cube. Where did I plug in u? Well, I got to here. Okay, so secant x is u. This is u squared minus 1. That's u squared, and that's du. So far, so good? All right, let's go back to a relatively easy one and have you practice. Let's everybody do I don't believe I did that one yet, did I? Okay.
If you see an odd power, you won't be using it. So, one
Clue is when you see even powers of sines and cosines to begin with, you're going to use these, and when you see odd powers, you're going to use those. Okay? So we'll give you a step for those of you who didn't figure it out. You can make this sine x sine squared x. And then substitute for sine squared, and then you can do u substitution. Higher power will be u and lower power will be d. Well, I just said, if it's an odd power, you're going to use the 1/2, 1 minus cosine 2x, because it's an even power, use that. If it's an odd power, use the other substitution. Got that on recording. Right, Shani?
Yes.
Aye.
Aye.
All right, so from here, sine squared you could replace with 1 minus cosine squared. And now, don't take 1 minus cosine squared, put it back into sine squared, you're back where you started. Let u be cosine x, du will be minus sine x. So if u is cosine x, the higher power, du is negative sine x dx. So we get negative integral of 1 minus u squared. Because sine x dx becomes negative du. Yes?
How do you know what to do the...
Okay, so I'll repeat it, because people obviously didn't hear it. When you, it's okay, when you see the integral, and this is an odd power, you will end up breaking it apart into two parts of sines and cosines and using these substitutions. When this is an even power, you'll end up breaking it apart and using these substitutions. So as I said, one of the things about the families, and if you look in the book, and I'll put some stuff up online, you can see that it breaks it down basically into whether it's even powers of sine, even powers of cosine, odds, mixes, tangents and secants. There's about 6 or 7 families of these, okay? And once you see how to attack each family, it's very straightforward, and then you'll get very good at these. So how do I know to do this? When I see sine cubed, I get a sine and a sine squared. Since I know I can now turn this into cosine, I'll be able to use substitution because I'll have cosine and I'll have sine. If it's even and you try that, it just doesn't work. So that's how you know to do this. So this is negative u plus u cubed over 3 because I distributed the minus sign. And then you substitute back. You get negative cosine x plus cosine cubed x over 3 plus a constant. Yes? Why don't I let u be cosine instead of sine? Well, if I let u be sine, this would be 1 minus du squared, which wouldn't be very useful. So in general, when you see powers, higher power will be u and lower power will be du. Okay? In general. All right, I got one more fun one for you guys. Should I do it, Cecilia? Should I do secant cubed? Do I hate them enough? All right, because I hate all of you guys, we're going to do secant cubed. This is an entertaining one. So, and if you want to try to do this on your own, it's really fun. But we'll do it together. I won't start you. See, when you watch this in video, you may want to pause. But this will go up on video, and then eventually it'll be closed caption, which is keeping Shannon very busy. She's having lots of fun with that. Okay, what do we do for secant cubed? Well, what did we do with sine cubed? We broke it apart, so let's break this apart. And secant squared x is 1 plus tangent squared. So, how is that going to help? Well, let's distribute that. Secant x, because we could do the integral of secant x, it's that. Dx plus integral of secant x tan squared x dx. So I'm going to rewrite this up here for a reason. What did I not do? Nope. Okay, I got two integrals there. You go, but right there, make some minus sign in there somewhere. Secant squared, 1 plus tangent squared. Wait, I may have made a slight mistake. I'm sorry, I forgot, just start over. Rewind the video. I left out a step in the beginning. Sorry about that. Yeah, this is a confusing one, I promise. I know, tear that page out of your book and throw it at me if you want. I know you're thinking of it. Somebody will probably do it if I stand here long enough. Because then I'll turn around and I'll say, who did that? All right. Start again. My bad. Integration by parts. Gotta do integration by parts first. Which is going to be which? Well, I'm going to let u be secant x and dv be secant squared x. Why? Because if I let u be secant squared, the derivative's a mess. And if I let dv be secant x, I get this log thingy. That's not going to make my life easier. On the other hand, here, du is secant x tan x dx. V is tan x. Okay? So that means this is u times v, secant x tan x, minus the integral of v du, which is secant x tan squared x dx. See, look at that. Go, have I made it easier? Kind of. I went from cubed to squared. Now what do you do? Well, this is I'm going to take the tan squared and I'm going to make it secant squared x minus 1. So to rewrite this, I now have the integral of secant cubed x dx equals secant x tan x minus secant times secant squared plus, because minus secant times minus 1, plus integral of secant x. And remember that trick with adding back to the other side that we had the other day? I got minus secant cubed and plus secant cubed. So now I've got 2 secant cubed x dx. Isn't this one a great one? Secant x tan x plus secant x dx. Now it's easy, because we have integral of secant x. We memorize that. So 2 integral of secant cubed x dx is secant x tan x plus log secant x plus tan x plus a constant, and then just divide by 2. There's a fun one. And as you saw, since I had a false start, I sometimes have to go through these a couple times to remember the trick also. All right, I think everybody's had enough for one day. We'll see you on Monday.